Good morning, everyone, and welcome back to lectures. Let me start with a quick review of what we did last time. And just as a logistical comment, if you're watching this, then this is pre-recorded. Unfortunately, I had a scheduling issue. They moved one of my flights. So at the time you're watching this, if you're watching this at the time of the lecture, then I'm currently on a plane, so I couldn't have done this live. And I apologize for that. If you have any questions at any point, feel free to post them on Piazza. I will be actively monitoring this, and if necessary, I will hold extra office hours for you to ask all the questions. I don't think this is too necessary since we will have more than enough time next week to have probably around an hour just for questions on these things or to explain more examples because we are slightly ahead of schedule. So like I said, let me begin with a quick recap of what we did last time, which is the beginning of chapter 5, topology. We talked a little bit about what a metric is. A metric is nothing other than a function that measures distance between 2 points in a space. The only space we care about right now is Rn, which is defined at the bottom of the page, as you can see. And there's a very well-known metric for this, which is the Euclidean metric. This is how you measure distances between points, basically using this a right triangle to measure the length of the hypotenuse from some point to some other point, right? So here's an example in R2 from the triangle inequality. I did not prove that this is a metric, but everything that you need to prove that it is indeed a metric has been done in the past when I talked about the absolute value and stuff like that, right? So then we started talking about a very important and powerful idea called the idea of open sets, open and closed sets. So here's an intuitive example, and you can check that out in the last recording. I defined the idea of an open ball, and I proved that all open balls, I may have only done this for intervals, are open sets with this definition. So a set is open if every point that is an element of A is actually inside A. It's an interior point, right? You can surround it with a small enough ball so that the entire ball is still contained. There's an entire neighborhood, an entire cluster of points around this point that are still elements of A. So it's not something that is on the boundary and much less outside of A. Now, similarly, I defined a point of closure of a set A, which is simply a point that is glued to A. It is so close that there's no way to separate it from it by zooming in, because every ball, every radius around this point X always intersects the set, right? And we denoted the set of all these points of closure with a bar, an overline bar. This is called the closure. And here we have some examples. Some basic observations is that every set is contained in its closure, and the balls in R are simply just these intervals, right? Every open interval is open, and the exact same idea you can use to show that every open ball is also an open set, as the name would suggest. I don't know why I did this just for the open intervals. Now that I look at it, the same idea would have worked for proving that open balls are open sets. So you can definitely do that as well. Two important properties about open sets that are useful to construct new open sets is that if you take any number of open sets and you glue them together, you take the union, you still get an open set. But for the intersection, you can only take a finite number of open sets. And we proved this for two, but the same idea, or using induction, can be used to show this for any finite number of open sets. If you attended the last tutorial, you'll know that you cannot generalize this to infinite intersections, right? It is possible to find an infinite collection of open sets so that their intersection is no longer an open set. Okay, now let me continue to the next page. So let's do some more examples, but now of the closure. We already talked about open sets, so it's time to consider the example of the closure operation. Any set, for any set of Rn, any subset of Rn, it makes sense to consider the closure of that set. So let's look at some examples to see if we can understand what it means. The closure of the empty set is empty. Why is this? Well, there is no point in Rn, or particularly in R, that is a candidate for being a point of closure of the empty set, because you cannot ever intersect the empty set with anything, right? So no point can be a point of closure of the empty set. And that explains why there are no points of closure of the empty set. So this set is empty. Now, why is the closure of the real numbers, or actually I could have done this with an n, right? Why is the closure of Rn just Rn itself? Why is this set unaffected by the closure? And I can use a very cheap argument here, right? So the space that we're talking about is Rn. So everything is contained in Rn. So in particular, if this set, the closure, is contained in Rn, we already know that the other inclusion is always true. Rn is always contained. Any set is contained in its closure. So these two sets must be equal. And this doesn't even depend on the definition of closure, right? There's nothing to prove here. This is almost as obvious as the case for the empty set. Let's do something that is perhaps a little less obvious, even though I did mention it in the last lecture. If you take the open interval 0, 1, you can analogously do this for the open ball, and you take the closure, you take what you get is the closed interval, right? So everything inside the open interval 0, 1 is still in the closure, but we're adding the number 0 and we're adding the number 1. So if I make a sketch of this, then this is very simple, right? So we have the interval 0, 1, and the point 0 and the point 1 are points of closure. They're very close to the set. And to prove this, all you would have to do is pick a radius and show that for any radius around 1, there's always points inside the set. But this is easily achieved because this radius will always contain things that are smaller than 1, and therefore inside the interval 0, 1. And the same works for 0, right? So you can, if you want to practice writing these proofs, then this is a good exercise. It's probably the simplest non-trivial example of proving that something is the closure of something else. Let's focus now on something perhaps a little bit more complicated, or more abstract rather. If you have any set of Rn, or let's say real numbers, E, and if you take the closure twice, and by extension any finite number of times, then the result that you get is the same as if you had only done this once. So there's no point in taking the closure more than one time on a set, because it will not change the outcome. Taking it once will obviously change it. I just showed you an example where taking the closure gives you a bigger set. But if I took the closure 100 more times, it won't change the outcome. So let's prove this, because this is actually quite important and also interesting, right? So let's prove this. So how do we prove this? So we already know, because we already proved that, or we argued this last time, that any set is contained in its closure, right? So if I take the closure on both sides, well, in particular, E closure is contained in its closure, right? So we have that inclusion. So we have to show the other inclusion. How do we show that something on the right is also on the left? Well, let's just take an arbitrary element, x, and this is going to be in E closure. I want to convince you that x is in just E closure. So how do we do that? Well, by definition, I have to show you that x is a point of closure of E. So let's pick this point and let's pick an arbitrary radius, right? So what we want to show is that any radius around x will intersect E. And I know that it intersects E bar. So let's see if we can make this work. So since x is a point of closure of E bar, so an element of E double bar, that means that the ball centered around x of radius r intersects E bar. So this is non-empty, right? But if we pick a point inside there, so let's say pick something, so this is something in E closure that is also very close to x, then y is a point of closure of E, because it is in E bar. That's the definition of E bar, right? Now, there's something interesting to notice here. Y has an open neighborhood that we are talking about here, which is the ball centered around not Y, but X. So that open set must intersect E as well, which is what we're trying to show. Now, if we're being very formal, I haven't really showed you that it doesn't matter what open set we take. Right now, we only know that we have to take the open set centered, the open ball centered around the point. But we can easily adjust that in this case, even though it works for any open set, right? So how do we do that? Let me draw a sketch and maybe I can pull all this down, hopefully. So let's make a sketch of what is going on, and you'll see why geometrically this is actually very easy and we're pretty much done. So the situation is as follows. We have some point x, and we took some radius around x, and we know that there's some point y that is in the closure of E. This is y, right? So wouldn't it be enough to show that if we can just take a ball that still fits inside this larger ball, which we can obviously do, then that ball has to intersect E, right? So not to be excessively technical, let me just do this geometrically, right? So this is R, let's call this R prime. So pick R prime, and we did this in the past, right? We did this to show that every open ball is open, or with the interval. Like I said, it's the same idea. So pick a radius R prime, and you could explicitly define this. How would you do this? Well, you would have to measure the distance between X and Y, and then make sure that this radius still fits inside. But I think it won't really add anything to the proof if I give you more information how to pick this R prime, right? Such that the ball centered around Y of R prime is small enough that it will snugly fit inside our original ball, right? So then, given that Y is in E closure and therefore a point of closure of E, then this ball must intersect E, right? So the ball YR intersects E. And now we're done because whatever point sits inside there will also sit inside the bigger ball, right? Notice that if I take E and I intersect it with the ball YR prime, this is, like I said, contained in this larger ball, XR, right? This is, I maybe reference this. So this inclusion is because of that inclusion. Right, so if this is non-empty, well, then this one is non-empty. Is non-empty because it contains something non-empty, so it contains some point. And we're done. That's what we wanted to show, wasn't it? We took an arbitrary point x, an arbitrary radius, and we showed that it intersects E. That means that x is in the closure of E. So we're done because that means, therefore, any point x satisfying this, being in double prime, has to be in just one, sorry, not double prime, double bar has to be in just one bar, and the other inclusion was given. So these two sets are always equal. Other than the fact that this has some important ideas and important proving techniques, there are some interesting consequences of the fact that the closure of the closure is just the closure. Also, this is I think one of the additional exercises in the problem set, so I just solved that for you. Let's do one more example, and I'll tell you what consequences this has. Now, I know this isn't live, so I can't really expect an answer from you. What do you think the closure of the rationals should be? If you take the set of rational numbers in the reals and you take the closure of that set, what do you think that should give you? You already, maybe this was already mentioned in the tutorials, because it's an example of a set that is neither closed nor open. The rational numbers are neither closed nor open. They are not open because they cannot contain any ball, right? Any ball cannot consist just of just rationals because it has to actually be uncountable. And it cannot be closed because of what I'm about to show you right now. So this is actually the entirety of R. This is important for reasons that you might not realize now because all we are talking about is R, but not every topological space has this property that it has a very small set, like a countable set, like the rationals, that is still dense inside it, right? Just think about what this means. It means there's a very, very small set, right? The reals are uncountable. There's many more than rationals. And yet we found a very small set whose closure is already the entire space. So it's a small set that is everywhere, right? It's everywhere. In every open set of the reals, there must be rational numbers in a non-empty set, obviously. And this is called density. And there are also some exercises of this, I think maybe additional ones in the problem set. So this property is called density, right? Now, we already actually did the hard part of the proof. So recall from the construction of the real numbers that any xy reals, maybe I should say for any xy reals, there is a rational q that is between them, right? That's what the density means, and that is one of the first things we proved about the rationals, that they are dense, not just in themselves, but in the real numbers. I should look up the reference for that anyway. So what does this imply? So obviously the rationals are contained in the reals, and therefore taking the closure changes nothing, right? So the closure of the rationals is definitely contained in the reals. That's the space we were talking about. But we have to do the other inclusion. So take a real number. How do we show that this real number is in the closure of the rationals? Well, you take a radius, like we just did up here, take a radius and show that it intersects. And now notice that there is, by this property, there is some rational q that is inside the interval minus r. Okay, I think we should call it x minus r, x plus r, right? That's an interval, right? Those are those are two real numbers. So in between, there must be a rational q. But then we're done, right? Because this q is not only in this interval, it is in the rationals. And that means that x is a point of closure of q, and we're done, right? So the hard part of this proof is showing that between any two real numbers, you can always find a rational number. Now that I say this out loud, I'm not 100% sure we did this in the past, but I'm pretty sure we mentioned that during the construction, right? And if not, we can look at this next week in more detail as well. Okay, so that finishes the examples I had in mind for closure. And something that is very closely related is the, pun intended, is the following definition. So a set E is called closed if it contains its closure. Like I said, every set is contained in its closure. So this inclusion is really just an equality, right? If you have the inclusion, the other one is always true, so they must be equal. So a set is closed if it is equal to its own closure. There is nothing you can add to it by taking the closure. Everything that is closed to the set is already inside the set, which is why we call this closed, right? There's nothing you can add to it. So an example that we mentioned is the closed interval, 0 and 1. Everything that is at least 0 and at most 1. This set is closed because just writing the bar on top, we already showed that it is this, right? If you look at the top of the page, the closed interval is equal to the closure of some set. So taking the bar again won't change that. It is already the bar of something, and therefore it is closed, right? And the empty set in Rn are closed. We already showed this, right? Because if you take the bars, the closure, it's themselves. And we argued last time that both of these sets are open. So these are actually examples of sets that are both closed and open at the same time. And I've said this the last lecture as well. When you hear the word closed and open in topology, you shouldn't think of a door, right? Doors are either open or closed, but sets are not. right? Sets could be both or they could be neither. So keep that in mind. Just because something isn't closed doesn't mean it has to be open. Now, the closure of any set is always closed. Why is that? Well, maybe think about this for a minute. Either pause the video or maybe I should just pause myself. The closure of any set is closed because if you take the closure twice, you get the same set, right? That's what we just proved up here at the top of the page. If you take two bars at the same time, that's the same as taking one bar. And that's by definition what it means to be closed, that it is equal to itself with a bar on top of it. So the closure of any set is closed. Now, I know this might sound a bit convoluted. It is actually very, very simple ideas, but do try to spend some time building your own intuition around this because it's a lot of words that come together, and thinking about what the easiest way to prove these facts is might come in handy. Now, there is one more thing I want to mention about closed sets, and then we can move on to the next subject. Something important about closed sets is there is a way to think about the closure in terms of sequences. Sequences have been mentioned a lot in this course, but I did not really want to talk too much about them in topology, because even though they play an important role in topology, in particular real analysis, the entire goal of me teaching you topology is that I want to generalize the things that you will see in real analysis because I think it will make your task of learning those things easier in the future. So if I just talk about sequences, I will be doing things that you will have to do anyway for real analysis. On the other hand, if I don't mention anything at all about sequences, I'm doing you a disfavor by not showing you how these ideas are connected with each other. So let me remind you something that I'm sure you know, and if you don't, then this will be pretty much the number one topic you will study in real analysis. Okay, what does it mean for a sequence xn of numbers, of real numbers, or let's just say elements, vectors in Rn, to have a limit? And moreover, what does it mean for that limit to be some other point x? It simply means that every time you take a radius around x, let me draw this up. So this is the point x, and there's a sequence, right? So this could be x1, and sorry, we start with 0, x1, x2, x3, x4, and maybe it jumps further away, but eventually the sequence has to converge to x. So intuitively, what is happening is that it's like a game, right? You challenge the sequence by giving a radius. Then the sequence has to come up and say, well, eventually the whole sequence will be contained inside that radius, inside that ball. But then you come again and say, wait, no, I can do better. I can find a smaller, a harder, a more difficult radius to comply with. And then the sequence has to say, actually, I'm so close to this point x because I'm converging to that point x that I can still come up with an index that is so large that the entire sequence is eventually contained inside that ball, right? And another way to think about this is with the idea of zooming in, right? If I zoom into the point x, I should always be able to see points of the sequence. Because if not, well, eventually this point is separated. But if it's the limit, if the sequence approaches it, if it approximates it, if it converges to it, these are all synonyms, then it should have this property, right? So this symbol of limit is simply abbreviating the phrase. Every time you have radius, there must be an index that is so large that the rest of the sequence, starting onwards from that index, is fully contained inside that ball, if that makes sense. Now, I don't want to spend too much time thinking about this definition because, like I said, we don't really mention this in this course to the point that sorry, that it's not even talked about in the problem set, right? I can give you exercises about this if you're interested in taking real analysis, just let me know. But this isn't a crucial part of the course, or rather, it's something that I deliberately skipped, and it is for educational purposes. So it's not because I don't want you to learn this, but I think this is I think this is for your having your best interest in mind. Okay, so here's an example. The limit of the sequence 1 over n, so this is just a sequence of real numbers, 1 over n, is 0, the real number 0. Why is this true? Let's prove this using the definition, and you'll see why this is something you already know. This is just the Archimedean property, just written differently, right? So according to the definition, I have to give an arbitrary radius r, a real number, and somehow the sequence needs to give me a large enough index so that eventually everything is contained inside that ball. Now, why should this be true? Well, by the Archimedean property, let's just write it like this, by Archimedean property, there is, most of the times we don't even explicitly cite the Archimedean property because of how ubiquitous it is, but it is important, right? It is something that we should keep in mind because not every space has this property. And there's a big enough number that will be bigger than any real number that I want, right? So here, right now, I care about being bigger than this one because then 1 over n has to be smaller. Am I doing this right? Than r, or n starting at with this index. And then this part of the sequence is in fact contained. So 1 over n is in fact in this boundary, sorry, not boundary, in this ball, centered around 0 and with radius r. And so we're done because that's what we wanted to prove, right? For all n bigger than this very large index, the rest of the sequence is contained inside this ball. So the sequence 1 over n indeed approaches 0 as you would expect, and maybe if you've never seen a proof of this fact, well, now you know. It is not entirely trivial, right? We do need the Archimedean property. And a lot of people neglect this because 1 over n is usually treated as equivalent to this arbitrary r, arbitrary epsilon. Other people will call this r and epsilon, and it's the exact same idea. Now, why did I care about defining sequences? Well, here is an alternative way of defining or thinking about the closure of a set in terms of sequences. For any set of real numbers or any subset of Rn, the closure of E is exactly those points that are limits of sequences inside E. Now, I shouldn't perhaps prove this in whole generality, but I do want you to understand this idea. So let's try to do a very simple proof, one that is more geometric rather than anything else. And formalizing this can either be left as an exercise, or you can just trust that if you ever mention topology within a course of real analysis, then this is something you will definitely prove. So, so that you don't waste too much time doing it twice, I think this is a better investment of time. So let's understand the connection between these two ideas. Like I said, closure is everything that is close to E. Why would this be related to limits of sequences? Well, if you can approach something within E, even if it's not exactly an element of E, but if I can approach it and be as close as I want, it is capturing the same idea that this point is glued to E, right? It's closed, it's inseparable from E, because I can find points that are closer and closer and closer, and that's how you would construct such a sequence. So let's do the forward implication. Forward, actually, this isn't really an implication, this is an inclusion, right? So how do we prove that E bar is indeed equal to this other set? Which makes perfect sense, by the way, that set. Okay, so let's do this. I will write this in green because it's like a comment, right? Like a sketch. So let x be some element in E closure, and we want to show that x is the limit of some sequence. So how would we do that? How do we produce a sequence? We need to verify this existential quantifier. We need to produce a sequence in E that will converge to xn. So here is my suggestion to you. And this is where again, you will passively use the Archimedean property or a similar idea. So for every n, we might actually end up doing this with enough formality to be a valid proof, but let's just try to do it like this. So you have something here. Let me get rid of this. Here's the situation. Here's your set E, and here you have a point X that is somehow very, very close to E. It's in the closure of E. So what does that mean? It means that every radius around X intersects E. So wouldn't it be enough to just pick a point in every intersection, and we can just shrink down these circles, make them smaller and smaller and smaller. And every time we pick some point forming a sequence, that sequence has to converge to X if I pick the radii in the right way, because they're shrinking down on X. They're getting closer and closer, and so must the sequence, right? So for every n, pick xn as some element inside this ball, some element of E, of course, because E must intersect any ball, any open ball around X. So let's pick the radius 1 over n. Why 1 over n? I can pick anything I want, right? But it has to be a countable amount of numbers because I only want to generate a sequence, not something more complicated. So 1 over n seems like the easiest. You could pick 1 over 2 to the n or 1 over 2n or whatever. I mean, I guess technically, since the natural started 0, I should do something like that, but it's fine, right? So this set E intersects any ball, in particular that ball. So for any intersection, let's just pick some element xn. And then I'm done, right? Because xn, this sequence, is indeed contained in E, the entire sequence. And you can verify using like the inverse Archimedean property in a way that the limit of xn has to be x, right? And maybe this is the part that I leave as an exercise, but it follows from the construction. Basically, if you take any radius around x, you can find a ball of this shape with the natural number, smaller, and that one has to contain the rest of the sequence because these are shrinking in size, right? So it's pretty much the idea that whether we pick 1 over n or we pick r or epsilon as the radius, it's the same thing. It's an equivalent definition. So here we're done. This proves that I just constructed a sequence for you whose limit is x. So x is a limit point. I just showed you that every point of closure is a limit point. Let's do the other inclusion. So now we have to take a point in the right set. So it is a point such that there is a sequence in E that converges to it. So assume that the limit of some sequence is X, and this is always an element of E, right? All of these are elements of E for all E, for all n. Now I have to convince you that X is a point of closure. Why would X be a point of closure? Now, like I said, this isn't live, so I cannot really wait for a response from you. But this is also very easy. So let R be a positive real number, and we consider the ball of radius R around X, and I have to convince you that this intersects E. But by the definition of limit, this must contain the entire sequence, right? This ball must contain a tail of the sequence. So then xn is inside S for some large. I only need one element, but it contains all of them actually. All of them starting onwards from a point. But I just need one of them. Then this ball intersects E because xn is always an element of E. Oh, thus X is a point of closure. This is actually a formal proof. I don't know why I said I would just sketch this out. This ended up being a formal proof. I didn't really skip any details, maybe except this one I left as an exercise, but it's not a sketch, right? This is the formal proof. And that's how you show that these two definitions are equivalent. And some people, some textbooks define it using sequences instead of open sets. They say a set is closed if and only if every point, every sequence converging to a point has to converge inside the set. That's what closed means. If you have a sequence of points that converges and the convergence point is outside the set, then your set is not closed. Now, this has some interesting implications. Let's scroll up to the examples of closed sets or closures. If you look at the one at the top, the fact that Q bar is R according to the thing I just wrote down means that every real number is not just a point of closure of the rationals, it's a limit point of the rationals, because that's what I just proved, right? I just proved that everything in the closure is the limit of some sequence. But if the closure is R, that means that every real number is the limit of a sequence of rationals. We already knew that because I told you right at the end of the construction that every real number has even like a natural canonical way of being approached by rationals, namely the decimal expansions, right? For example, pi, which is 3.14, 16, and so on, can be approached by 3, then 3.1, then 3.14, and in this sequence of rationals approaches pi, and you can do this for every real number. So every real number is approached by some sequence of rationals. But this isn't the only example where this will be useful. But I hope you found this interesting. In our next subject, I will pause the recording here, but the next subject will be a slightly more interesting, more complicated example. And since this isn't live and I'm not answering any questions, I will try to do this lecture a bit shorter so that you can just watch it in your own time and have enough time to reflect on this and ask questions. But we are, like I said, slightly ahead of schedule, so everything's fine with that. Okay, so see you in the next video.